Hello, everyone. I thank you for joining us today. Today's topic will center on plate tectonics. Let's first talk about how our understanding on plate tectonics came to be. The first piece of evidence surrounding plate tectonics comes from the fossil distribution. Many ancient organisms were discovered as fossils, and these fossils were identified in many different parts of our world. For example, the Lystrosaurus was an ancient land reptile. Their old habitats were known as Africa, India, and Antarctica. Out of the many ancient fossils found, fossils such as the Lystrosaurus proves the theory that continents were together in prehistoric times. This is because it is a land animal, and the fossils were found in different regions of the world that aren't associated with its habitats, of which I listed above. Therefore, being a land creature, there is no way that it could have ended up in different continents, as it surely couldn't swim across vast oceans. This supports that our planet is made up of plates, and although the continents were once all connected, they are now mostly separated, making up the present world we have. Furthermore, 300 million year old glacial rocks are another determination for plate tectonics. When glacials go over land, they scrape and leave evidence that they were once there. Rocks showing scratches, like there are located in New York, show that a long time ago, glacials were there, hence proving the separation of our continents through time. Now we will talk about the theory of plate tectonics, which revolved around the continental drift, and I talked about the idea that continents move horizontally over Earth's surface. This theory was orchestrated by Alfred Wegener. Although we believe in this theory today, it was majorly ridiculed in the past when we didn't have enough evidence supporting the fact that continents could drift. However, in 1940 to 1970, there was added evidence through seafloor topography, the findings of oceanic crust versus continental crust, paleomagnetism, and earthquake and volcano distributions. Let's talk about ocean bathymetry. So in the ocean, there are mid-ocean ridges, which are underwater mountain ranges associated with fracture zones. Their average depth is around 2.5 kilometers. There are also trenches, which are the deepest parts of the oceans. The deepest location on Earth is the Mariana Trench, which is 11 kilometers deep, making that a greater size than even Mount Everest. Lastly, there are abyssal plains, which are vast flat areas in between ridges and trenches. Their average depth is 5.5 kilometers. Let's quickly touch upon paleomagnetism, as it is an important thing to know when talking about plate tectonics. Here, magnetic materials in volcanic rocks record the Earth's magnetic field as the rocks begin to cool. Once a rock cools below 600 degrees Celsius, it starts to become solid to the point where its magnets won't change their direction. They usually point to the North Pole. Just a fun fact. Basically, we can take a rock out of the ground and see what the magnetic field was doing at the time it cooled. We are essentially assessing rock isotopes here. This entire process is called remnant magnetism, and it is important about building onto our knowledge on plate tectonics and what they were doing millions of years ago. Now that we have familiarized ourselves of what plate tectonics are and how the theory developed through time, let's talk about the types of boundaries found. The first one being convergent boundaries. This process is when an oceanic plate subducts under a continental plate. Subduction in this case means diving underneath another plate. The oceanic plate dives underneath the continental plate due to it being more dense. The result creates deep earthquakes on the edge of the subducting region. Another type of plate boundary is the divergent boundary. This occurs when two plates diverge. Their crust gets thinner. For example, as two continental plates diverge in opposite directions, their crust gets thinner, creating something called a rift valley, which is filled with water. Lastly, there are transform boundaries, where two plates move in opposite directions while still touching each other, so like this, basically. This could be presented as fracturing perpendicularly. So, plate tectonics essentially are very important to understand because they contribute to the causings of earthquakes and tsunamis and volcanic activity. An earthquake is the sudden movement of Earth's crust. Earthquakes occur along fault lines, cracks in Earth's crust where tectonic plates meet. They occur where plates are subducting, spreading, slipping, or colliding. As the plates grind together, they get stuck and pressure builds up, essentially. Finally, the pressure between the plates is so great that they break loose. Depending on how much pressure has built up, the ground may tremble slightly or shake forcefully. Scientists describe the intensity of an earthquake using the Richter scale. It measures earthquakes on a scale of 1 to 10. People barely feel a magnitude of 3 earthquake, and windows might rattle at magnitude 4. A magnitude 6 earthquake is considered major, causing houses to move and chimneys to fall. The largest earthquake on record had a magnitude of 9.5, completely decimating the location it occurred in. Tsunamis can also be generated by earthquakes on all of these faults that I listed earlier, but most tsunamis and the largest result from earthquakes on reverse faults. These tsunami-generating earthquakes originate mainly in subduction zones, remember where one plate goes under the other, where tectonic plates collide and one is forced under the other, as I just mentioned. If big enough and close enough to the ocean floor, the energy from such an earthquake can cause the ocean floor to suddenly rise or uplift, or fall, subside. It is the sudden vertical displacement of the ocean floor that typically sets a tsunami in motion. As the ocean floor rises or falls, so too does the water above it. As the water moves up and down, seeking to regain its balance, a tsunami is born. Understanding how plates move and what type of boundaries are present in our planet can help us predict when these natural disasters will likely occur, and thus we can take active measures to prepare societies for the upcoming destruction. And now I hand over the presentation and lesson to Michael. Thank you.
For this portion of the lesson, you will all participate in an activity about plate boundaries. I have created a worksheet for you all to complete individually, and I will ask you to pause the video at certain points and fill out the designated areas of the worksheet. Alright, let's begin. For the first activity, you are going to draw arrows in the boxes in the first table on the right side of the worksheet, corresponding to the ways in which the different types of plates move. I'm going to ask you to pause the video now and fill in the first 3 boxes on the right side of the table. Here's a hint. You should be drawing 2 arrows in each box representing 2 plates moving toward each other, away from each other, or past each other. Take your time, no rush. Alright, I hope you all have your arrows drawn. Now let's go over the answers. For a divergent plate boundary, you should have arrows drawn moving away from each other, as they are diverging or moving apart. For the convergent plate boundary, you should have arrows moving toward each other, or converging, or moving together. For the transform plate boundary, you should have drawn arrows moving alongside each other, sliding past each other just like my hands. Alright, let's move on to the next section. Don't worry, for this section, I'm going to be telling you the characteristics of the 3 types of plate boundaries, and you're going to write notes in the corresponding boxes about the main characteristics you heard. To begin, for divergent plate boundaries, they are characterized by having volcanic activity and seafloor spreading. These boundaries often occur at the mid-ocean ridges. For convergent plate boundaries, subduction occurs as one plate goes under another as they collide, creating trenches, and also often characterized by volcanic activity and earthquakes. For transform plate boundaries, the plates slide past each other and often cause earthquakes. Alright, I hope you guys enjoyed that activity. Let's move on to the final part of the lesson. Although the theory of plate tectonics help explain the origin of many features near plate boundaries, it does not seem to explain the origin of intraplate features that are far away from any plate boundaries, such as hotspots, seamounts, and table mounts. Areas of intense volcanic activity that remain in more or less the same location over long periods of geological time and are unrelated to plate boundaries are called hotspots. For example, the continuing volcanic activity in Yellowstone National Park, located within the North American plate, and Hawaii, located in the center of the Pacific plate, is caused by hotspots. The plate tectonic model infers that hotspot volcanic activity is caused by the presence of mantle plumes, which are vertical, tube-shaped areas of hot molten rock that arise from deep within the mantle. Many areas of the ocean floor, most notably on the Pacific plate, contain tall volcanic peaks that resemble some volcanoes on land. These large volcanoes are called seamounts, if they are cone-shaped on top, like an upside-down ice cream cone. Some volcanoes are flat on top, unlike anything on land, and these are called table mounts. Until the theory of plate tectonics, it was unclear how the differences between seamounts and table mounts could have been produced. The origin of many seamounts and table mounts is related to the volcanic activity occurring at hotspots. The origin of others is related to processes occurring at the mid-ocean ridges. Because of seafloor spreading, active volcanoes, or seamounts, occur along the crest of the mid-ocean ridge. Some may be built up so high that they rise above sea level and become islands, at which point wave erosion becomes important. When seafloor spreading has moved the seamount off of its source of magma, whether it's on a mid-ocean ridge or on a hotspot, the top of the seamount can be flattened by waves in just a few million years. This flattened seamount, now a table mount, continues to be carried away from its source and, after millions of years, is submerged deeper in the ocean. Frequently, tops of table mounts contain evidence of shallow water conditions that were carried with them into the deep water. The study of historical changes of continental shapes and positions is called paleontology. It's difficult to say with certainty how long plate tectonics has been operating because our planet has been so dynamic since its very early history, regularly recycling most of Earth's crust. However, recently discovered ancient volcanic rock sequences uplifted onto Greenland show telltale characteristics of tectonic activity and suggest that plate tectonics has been operating for at least the past 3.8 billion years of Earth's history. Plate motion has typically been assumed to be an active and continuous process, with new seafloor being constantly formed while old seafloor is being destroyed. Recent research, however, suggests that plates may move more actively at times, then slow down or even stop, and then start up again. The geographic positions of the continents and ocean basins are not fixed in time or place. Rather, they have all changed in the past and will continue to change in the future.